picture this. You're an hour into your A-level maths exam. You've just burned through a 6-mark integration question. Okay? You had to do integration by parts twice in this question, and somehow in the second round, you lost the minus sign. And now the whole thing unravels and you have to do it again. Your brain hurts and your hand hurts from all the writing. But meanwhile, next thing you know, the person next to you has already moved on. And that's because there are some shortcuts that most A-level students never learn. Methods that give you the exact same answer in just a fraction of the time. Okay, so today I'm going to show you 3 of them. The first turns repeated integration by parts questions into a 30-second job. Okay, the second is a way of drawing triangles on a cast diagram to ensure that you never get a trigonometry equation wrong again. And the third is to save you so much time when basically doing the chain rule that you'll never look at the quotient rule the same again. Let's start with integration by parts here. Okay, because we know the formula is that the integral of u dv is equal to uv minus v du. Okay, now for x e to the power of x, 1 round is fine, you can do that. But what about x squared times e to the x dx? Now you need to do by parts twice. And for the integral of x cubed times e to the x dx, well, that's 3 times. Okay, so each round you're relabeling u and dv. Okay, differentiating, integrating, substituting. Okay, and by the end, if you make a small slip, the whole thing collapses. So what if you could do all 3 rounds at once in a single table? Okay, so here's how you do it. If you set up a table with 3 columns, you've got the sign column, which will go plus, minus, in that order. And then you've got D for differentiate and I for integrate. D is going to be your U, okay? Meanwhile, dv by dx is going to be the integration column. If you don't know how to pick u or dv, make sure to watch my integration by parts video. That was quite good. It goes through exactly how to pick u and dv. But anyways, what you need to do here is you're going to differentiate the d column down until you get to 0. Okay. Meanwhile, you're going to integrate the integration column the same number of times. Okay, but you stop when you get to 0 on the differentiation column. Then what you do is you read the answer by going diagonally. Okay, so you're going to multiply each d entry by the I entry, 1 row below it. Okay, apply the sign and add everything up. But wait, now we have another problem. I'm not sure if you've noticed it yet. What if we have both a u and a dv by dx that just keeps on repeating and never goes towards 0? Okay, so let's take the example of e to the x sine x, the integral of that. Okay, now because none of these, either by differentiating or integrating, none of these are ever going to hit 0, so it doesn't matter, you know, which one we apply as which here in this example. So Lie8 doesn't really apply. So let's let u equal e to the x and dv by dx equals sine x. Okay, we put that in the rows. What we get, okay, in the differentiation column, so it's e to the x, e to the x, e to the x. Meanwhile, in the integration column, we get sine x, negative cosine x, and then negative sine x again. So how do we go about solving this now? Well, what we're going to do is we're going to say, look, read the diagonals as normal. Okay, so we're going to say the integral of e to the x sine x dx is going to equal plus e to the x times negative cosine of x. Okay, then minus e to the x times negative sine x. Okay, now for the next part here, we're going to say, look, well, we've got a plus and we've got e to the x and negative sine x at the bottom row. Okay, so what I'm going to say is I'm going to say plus the integral, okay, because I'm not going any further here, I'm going to say plus the integral of e to the x times negative sine x. And as a result, what does that give us? Well, that gives us the integral of e to the x sine x dx, okay, that's going to equal the negative e to the power of x times cosine of x plus e to the x sine x minus, minus e to the x sine x dx. And if we let the integral of e to the x sine x dx equal I, we can flip this over, and so we got 2i is equal to negative e to the x cosine of x plus e to the x sine x. Okay, so now moving on to trig equations. Here's what usually happens. You solve for sine theta or cos theta, plug it into your calculator, and you get one answer. Now obviously they'll often want a range of answers, right? But the issue is sometimes it's difficult to work out how exactly to get the different answers. Even if you're doing the, your plus n times 2 pi or plus n dot pi, sometimes that can get confusing. Okay, so here's a way, a bulletproof way. It's very easy to really simplify things down for yourself and ensure that you're always getting the right answers. To take an example of this, to illustrate this the best way possible, let's say we have 2 sine squared theta plus sine theta is equal to 0. Okay, and that's from 0 theta to 2 pi. So that's our range. Now the first thing we're going to say is, okay, sine theta is equal to 0. Okay, because if we take out sine theta, we get sine theta, then we've got 2 sine theta plus 1. Okay, so we've got sine theta equals 0, so therefore we've got theta equaling 0 or pi. Meanwhile, we've got 2 sine theta is going to equal negative 1, which means that sine theta is going to equal negative half. Now make sure to pay attention to this bit, because this is where people can slip up really easily, and that's what we're trying to solve. So this is really important. If you recall, sine theta is equal to negative 1 over 2, okay, because 2 sine theta was equal to negative 1. Therefore, what does that mean? Well, sine theta is equal to opposite over hypotenuse, remember? So if we've got our cast diagram here, which represents our Cartesian plane in a way, and we've got negative 1 over 2, okay, and negative 1 is our opposite, that means our negative 1 is going to be representative of our y coordinate. Okay, meanwhile 2 is going to be the hypotenuse. So therefore, if we draw this on our Cartesian plane here, what that means is we're going to show that we have negative 1 on the y, 2 is a hypotenuse. Okay, and this also corresponds to our cast diagram labeling, right? This is just a bit more intuitive, but as you can see from the cast diagram labeling, we are putting the triangles in where sine is negative, okay? Because that is excluding the S and A quadrants. But drawing this triangle really helps things out, okay? Because what we're going to do now is say, listen, we've got our triangles, we've got theta, okay? So therefore, we can say that sine, or better yet, arcsine of 1 over 2, what's that going to equal? That's going to equal pi over 6. And the reason why I've done 1 over 2 instead of a negative 1 over 2 is because we're going to get a reference angle first. Because inside this little triangle, we're going to pretend that everything's normal and there's no minuses around us. We're just going to work out our reference angle. Okay, and that's pi over 6 inside that triangle. And from this point, guys, it's quite simple, because all we have to do is look at our cast diagram and say, well, look, we know in the t section that represents pi plus theta. Okay, and we know that theta here is pi over 6. Okay, and so what we're doing really is we've got pi going over as 180 degrees, and we're just adding that extra section on theta, which gives us 7 pi over 6. In a similar vein, in the cosine section, we've got our theta is pi over 6, but we've also got our 2 pi looping around 360 degrees. So that represents a full revolution there, but we're taking away that little slither that is pi over 6. So as a result, our answer there is 11 pi over 6. And as you can see, that means that we've got all of our solutions here. Okay, and by drawing that triangle, we've been able to make things a lot easier for ourselves. Alright guys, so now the last one is just kill the quotient rule. Just kill it. Because you know the equation, right? It's f dash g minus fg dash over g squared. And the thing is, it is a pain to use. Okay, it's easy to mess up the order, and the g squared on the bottom can result in just a massive fraction that needs simplifying and just messes everything up. So what if I told you that you never actually need this thing, ever? Alright guys, so this is a pretty easy one, because think about it. Every single quotient, f of x over g of x, can be rewritten as a product. Okay, so as a result, we get f of x over g of x is equal to f of x times g of x to the power negative 1. Okay, so this is really just the product rule now combined with a chain rule if we need to. And here's why this is better. Because the product rule is symmetric. Okay, we don't have to remember which rule comes first, also which term comes first, and at the same time we don't have an annoying g squared at the bottom. So it's a lot more simple. So to give an example, if we have x squared over sine x, okay, and we need to find d dx of that, instead of using the quotient rule and having to remember which way is which, this time we can just rewrite it. We can say that we get x squared times sine x to the power negative 1. Now, as a result, when we just apply our product rule here, okay, we apply it carefully, we just get 2x over sine x minus x squared cosine x over sine squared x. Okay, so obviously we're getting the same answer here, but we've had to remember a lot less. And when you're doing the exams at, at scale, lots of volume, and you've been doing it for like an hour and a half on the actual day, and maybe this is the last question, you don't want to be remembering and misinterpreting the wrong formulas. You just want to have something simple that works every time.